Okay, so question 6a asks you to find the value of k for which there are infinitely many solutions to this system of simultaneous equations up here. So we need to note that infinitely many solutions occur when we've got the same gradient and the same c value for two lines. So they sit on top of each other exactly. So they are parallel, indicated by these little arrows, and their c value is the same. So we want two lines where y equals mx plus c, with m being the same and c being the same. So to do this, I would suggest a matrix approach. Generally with simultaneous equations, that's a good starting place. So our matrix approach will let us express this like this. So the coefficient matrix is k for the first x here, minus 3 for the y, 4, and k plus 7, x and y, and we know that they're equal to k plus 3 and 1. Alright, so the next thing we can do is we can use the determinant of this matrix here. So we're going to calculate the determinant of this. So why do we want the determinant? Well, if det A equals 0, then that says that there are either infinite or no solutions to the system of equations. Alright, so calculating the determinant of this, we're just going to have the determinant equals d minus bc. So AD is k plus 7 minus BC, so minus 4 by minus 3. So the determinant is given by k squared plus 7k, expanding that out, plus 12. Now we want to find out when this equals 0. So again, it's a quadratic, so we should look to factorize first. So to do that, we're just going to pop k here and k here. And we're going to find a couple of numbers that can sit next to k that add together to give 7 and multiply together to give 12. So the multiples of 12 are, 1 and 12, 2 and 6, 3 and 4. So if we were to add these guys together, which one gives 7? Well, that gives 13. That guy gives 8. So 7 is here. This is the one we want to use. So we're going to insert plus 3 and plus 4 into that expression there. So I'll just get rid of this to give myself some writing space. Hopefully you can look that up later if you need it. So the Null Factor Law says that if this is the case, then k equals negative 3 gives 0, or k equals negative 4. They both give 0. Now the trap with this question, and I dare say a lot of the kids that got to the 1 mark stage probably fell into, was that they didn't actually validate their solutions. So that's the step we've got to do now. We've got to do some validation. We've got to check if it gives infinite or no solutions. So to do this, all we have to do is try out k equals negative 3 and k equals negative 4 in our equation. So the k equals negative 3 case gives our two equations as being negative 3x, negative 3y equals 0, and we get 4x plus 4y equals 1. So hopefully you can see that if we rearrange those in the form of y equals mx plus c, they're not the same. In fact, just do it really, really quickly. We would get minus 3y equals 3x. So we'd get y equals negative x for the first one. And for the second one, we'd get y equals x plus a quarter. Negative x plus a quarter. So they have the same gradient. Oops, just make that 4 better. They have the same gradient, -1, but a different y-intercept. So they're going to give no solutions if we graphed them. One would look like this. I'll actually do it in the colors for you. So the orange graph would look like -x, and then the green one would be -x plus a quarter. So they give no solutions. So we can automatically discount that as giving infinite solutions. So now we validate the k equals -4 case. So if all goes to plan, hopefully this should come out right for us. So we get -4x minus 3y equals -4 plus 3 is -1. And down the bottom we get 4x plus 3y equals 1. So if we multiply this whole side by -1, it would equal this one here. So they have the same equation. So actually I'll write it below just so you can see. So -4 by -1 is 4x. -1 by -3 is plus 3y. And -1 by -1 equals 1. So because these two are exactly the same equation, that means they are like this. Oh, actually, we won't do it on axes. I don't know exactly what they look like, but they are on top of each other, like that, and parallel. So now we've found the values of k for which there's an infinite number of solutions. So that was k equals -4, and we know that no solutions occurred at k equals -3. So now part B asks us to find the values for which there are a unique solution. So this is where the determinant does not equal 0. So we had det equals 0 for k equals -3, k equals -4. And that was the no solutions or infinite solutions case. So we want k is an element of everything, so the reals, excluding the set of -3 and -4. And this guy here is your solution. It will give you unique solutions for the system of equations. That is, they would at some point intersect at a unique solution.